Hi, it's Renata here. If it's your first time here, welcome to my channel, The Quanti Girl, where we are going to talk about some topics in quantitative finance, in pure and applied mathematics, in Python programming, and sometimes about music, because I'm a PhD in mathematics and a financial quantitative analyst that is also a violinist, and I'm here to share with you some of my experience. Today, we are going to code in Python the Bellman equation in a context of a tool of dynamic programming for finding the optimal allocation of assets in a portfolio. So just keep watching the video and let's code it together. Before we start coding, let's take a few words about the Bellman equation in our context of portfolio optimization. In the world of investing, finding the optimal portfolio allocation can be a hard task. But what if there was a mathematical equation that could help you navigate through the complexities? One possible answer is the Bellman equation. As its core, the Bellman equation breaks down the decision-making process into smaller, manageable steps, allowing investors to make informed choices. The Bellman equation in our context of portfolio optimization takes into account several factors like risk, return, and correlation between the assets. By optimizing these parameters, investors can construct a portfolio that maximizes the expected return while minimizing the risk. Imagine you have a set of assets with different risk return profiles. The Bellman equation helps you determine the best allocation of funds to each asset, taking into consideration your investment goals and risk tolerance. Whether you are a seasoned investor or just starting out, the Bellman equation provides a systematic approach to building a robust portfolio tailored to your needs. So now let's code in Python the Bellman equation in a context of optimal portfolio allocation. So the first thing that you need to do is to import the libraries that we are going to use. And today, the only library that we are going to use is the NumPy library to deal with the arrays elements. So now let's build a function that is the Bellman equation in our context here. So let's define a function. Let's call it Bellman equation. And this function arguments are uh, a returns matrix that we will call R, a discount factor that we can call gamma, the maximum number of iterations for the algorithm. Let's specify it as 1000 and a tolerance. So first let's take the length of the returns matrix. let's call it n. Now we are going to define two vectors to be filling during the iterations. So let's call it VOD vector and VNew vector. And to initialize it, we are going to fill them with the zeros, and the length of these two vectors, VOD and VNew, is the same length as the returns matrix. Okay. Okay, we also need to initialize the vector of policies. Let's call it policy, and we are also going to fill it with the zeros. So now we started to build the iteration of the algorithm. So we have two loops, one for to guide the algorithm if he's already reached the maximum number of iterations, and another loop for the actual, now it's really the uh, Bellman equation. So we need here a second loop, and we are going to iterate over the length of the return matrix. So in order to have the Bellman equation, we are going to initialize a new vector, and we are going to update this vector during the iterations. So let's call it vtemp. Let's fill it with the zeros, and now let's build the Bellman equation. So now we update the vtemp vector for the J interaction. So we take this element of the return matrix, and we add the VOD value of the iteration discounted by our gamma discount factor. Okay, now we need to update the v new vector inside the I iteration. So let's see the indentation here. Okay, the indentation is for the I iteration, so it's here. Okay, let's update our v new vector, this vector that we initialized here for the I iteration. So we want the the maximum number of the iteration. So what we need here is the maximum of this vector here. Okay, so now let's build a function to check if we reached the tolerance level. So if you don't reach the tolerance level, then we continue updating the VOD vector, and if we reach the tolerance level specified here as parameter of the function, then we break the algorithm. So let's write it. We need to take the difference in absolute value of the new value and the old value. So we need to take the absolute value of the difference between V new and V old, and compare it to the tolerance level. So if you don't reach the tolerance, we update the VOD vector. And so in this condition, the VOD vector is the updated v vector that we are calling here as v new. Okay, and finally we need to return the value and the policy. Let's run the equation. Okay, so now let's uh, build an example here to apply the function, the Bellman equation function that you built in this cell. So let's define a returns matrix. So let's just define some returns here. And let's define a final array, a third array. Okay, so we have here our matrix of returns. Let's now define a discount factor. Let's define it as 0.9. And finally, let's call the function Bellman equation in order to find the optimal values. Okay, let's print the optimal values and the optimal policy. Okay, let's run it. Okay, let's fix it, the code here. I think it's okay now. So we have here the optimal values and the optimal policy. It's just an example, so you can play with your own returns matrix and the discount factor. Let's suppose it is 0.3, and let's run it again. So we have built our code here that defines a function called Bellman equation that takes a returns matrix R and a discount factor gamma as input, and it returns the optimal values and policy using the Bellman equation. It iteratively computes the optimal values until the convergence using a specified tolerance level and a maximum number of iterations that we specified here as these values for the tolerance level and 1000 maximum number of iterations to until the convergence, and finally it prints out the optimal values and the optimal policy. So you have here the generic code, so you can play with your own arguments here for number of iterations, level of tolerance, your own returns matrix, the discounting factor that you want, and that's it. That's all for today. Hope you like the video. Don't forget to hit the like button because it helps me a lot. And also, don't forget to subscribe to the channel so you can know when I upload the next videos. See you guys in the next video. Bye!